So, in the last this thing I talked to you about a little bit about sedimentary rocks, metamorphic rocks, deformation, fabrics and metamorphic rocks. Now, I introduce you to a concept which is a very important concept in geology. Maybe from what I say you will not get the full implications or ramifications of it, but it's important to introduce you to a term. Now, this term is called unconformity. The term is called unconformity. What is it about unconformity, definition-wise? Unconformity is, and mark each of my words, unconformity is a plane of erosion or non-deposition. Once again I repeat, unconformity is a plane of erosion or non-deposition. In effect, it means a loss of geological record. Sounds a little vague, but let's say we have a table on which there is a rack, and on which you have arranged books, say books in an office. Say books in an office. This is, say for example, 1999, 1998, 1997, and say 1996. So say this is an office, some office record, yearly office record. 1996, 1997, 1998, 1999, 2000. Now, say, for some reason, this is no more. This is no more. There is a little gap and there is nothing in between that. What could have happened? Either this file was not kept there ever, or it means that yearly record was never there. Right? Or there could be another possibility. The record was there, but it was lost or somebody took it away. Have you understood? When there was no record, it means, when we come to rocks, it means something else. And it was there, but somebody took it away. So effectively it's lost. Means another thing. Having said this, we come to rocks. So say for example, let's say this is a crust. And you know you have the crust is roughly about 35 kilometers on the continents. You know, under oceans it's smaller, 5 to 7 kilometers. And this plane is called the moho. The morovisic discontinuity, and this is the main. And this is the crust. And just to make a little matters, there's a tree on it. So that's the Earth's surface. So there's a geologic section. Let's say because of some tectonic process, there is a strain developed this way. So what will happen? If it is stretched, then this crust this now becomes the structure of the crust. And this is the moho. And here you see a depression occurring. Now, the moment you have a depression and there are elevated lands on the surface, water or fluvial sediments will bring in sediments into this basin, right? Because these are at higher gradients, and there's a basin, so material will start to deposit in the basin. If we amplify this basin, and material is being transported from both directions, so you will have precipitation of sediments, and sediments will be deposited below the water level. Above the water level there cannot be any deposition. So you have A, B, C, D, E, where A is the oldest layer, B is the younger layer, C is younger, the youngest is E. Now these sediments that were deposited from bottom upwards, the direction of younging is this way. Direction of younging is this way. This is how the sediments are being put. Now, if there is no break in between, they record the sediments, essentially record a time zone in which these sediments were deposited. Have you understood? So this gives you a continuous geological record in time. Have you understood it? Now say for example, due to some reason, this sediment is, okay, let's do a simple one first. Now you know during the monsoon there is a lot of rain, and so materials are deposited much more during the monsoon time. But during the summer times, when there is less rain, some of the rivers dry up, their beds dry up. So what happens? In one monsoon and later periods, there is deposition. But as we approach the winter and come to the summer, where there is hardly any water in the river, there is a time when there is no deposition, right? When there is no deposition, that time is lost in this sequence. Have you understood? So, it is as if the file was never there. There was no record ever. Have you understood? There was no record ever of the file. It was never recorded. Maybe the whole office was closed because of COVID infection. There was no record. There was no official record of it. Similarly, when you have monsoons and sediments coming, and during a particular summer when the river dries up, there is no precipitation of sediment. And so that time is lost. Again during the monsoon, there is a new deposition. So there is a loss of geological record. Why loss? Because there is non-deposition of sediments. Have I got this clear in you? Non-deposition of sediments. That is why you did not precipitate sediments of a particular time. And that gives you, that is a plane that separates the two monsoons, the time that is lost. It's a plane of non-deposition. Have you understood? Now let's say, sometimes it might happen that sediments are being deposited in a depression, and due to some reason, the depression are uplifted so that the sediment thickness, the sedimentary layer, comes above the surface of water, above the mean sea level. What will happen then? Let's say, let's look at it this way. A theoretical photograph, a theoretical sketch and then we can look at it. Say for example, we have a situation like this where there is sediment E, B, C, B and A. Have you understood? But now what happens, because this is elevated portion, materials will be removed by this water? Yes or no? Why? To the places that are low. Water will drag down materials from the high. Just to give you an example, if you happen to climb up the Mount Everest and you go up to the peak of the Mount Everest, the rock that you will pick up was formed in a big ocean called the Tethyan Ocean. So it's essentially a marine sediment that was deposited and uplifted to that height. Because of tectonic process, you know, it's because of a subduction. I showed you the photographs before. There was the Indian plate subducting below the Chinese plate or the Eurasian plate, and you have a tremendous amount of compression that caused the materials to rise up. But that rock at the tip of the Everest, that was formed at the base of the ocean, the Tethyan Ocean. Now here you see what will happen. Materials from the top will be eroded. Have you understood? So you will have a record of a part, but a part of it will be eroded. And then as the material goes down, as the section goes down below the water, there will be new deposition. Have you understood? Now think what has happened. A, B, C, D, E formed during a time frame. Now D was removed by erosion. It was carried away by the rivers, by the water. And B and D was removed. So what has happened now? There was a record, but that record was removed by erosion. Have you understood? So it is, this file was there, but it was removed. So this is also, so if ABC is there and DE is not there, and then there is a surface above which you have M, N, O and P. See, in between that you have a sequence of sediments which were record of a particular time, but right now it has been eroded away. And so this is called, so this surface that demarcates that loss of time is an erosion surface. This is not a surface of non-deposition. In non-deposition there is no deposition. In erosion there is deposition and then erosion. So a plane of unconformity is called the zone of a plane of erosion or non-deposition. The file was there, taken out, or the file was never placed there because the office was closed for 1 year. So there was no official work due to some lockout, something unnatural, that an office was locked for 1 year. Now this is called an unconformity. Why it is important? Many of the events that you see around you on a local scale, they are not happening on a local scale. You see it because you are in a local, your view is local. But if you go global, you will see many of these unconformities, major unconformities, can be tracked across the world or major parts of the world and then be used for correlating different continents, different time zones. They can be used. So this is what I am telling you is unconformity. It is essentially a plane, a feature that you see in the rock, which is a plane of erosion or non-deposition. And the meaning of it is that it is a loss of geological record. Or in that time, for a particular time span, there is no record. That's all what unconformity is. Physically, it's an erosion, plane of erosion or non-deposition. Philosophically, It is a record of loss of time. Now, there are different types of unconformity, and I will tell you them briefly. There are something called non-conformity. Non-conformity. In a non-conformity, this is stop. In a non-conformity, you have a situation. Unconformity planes are given by a vary line. Below this, you have, say, an igneous rock. Have you understood? And say an igneous rock. Or it could be a metamorphic rock. The underlying rock strata is a non-sedimentary rock. So it could be an igneous rock, it could be a metamorphic rock, it won't be a volcanic rock, it would be a plutonic rock. Right? And on that, you will have sediment deposition this way. A, B, C. Non-conformity is this plane. So, sedimentary rocks are deposited in horizontal layers above a non-sedimentary crustal section composed of igneous plutonic rocks or metamorphic rocks. And this is the plane of erosion, never a non-deposition, because below this there is no sedimentary rock. So there is no question of deposition. So this is always a plane of erosion for non-conformity. So non-conformity is when the underlying rock below the erosion plane is a non-sedimentary rock or igneous or a metamorphic rock, and the overlying layers are sedimentary in nature. And you can imagine A is old, B is younger, C is the youngest. That's what is a non-conformity. The next term that is used is angular unconformity. Angular unconformity. Sorry, unconformity. Again, this is a section. This is stop. This is what it is. What has happened? Angular unconformity occurs between two sets of sedimentary rocks. Two sets sedimentary rocks. The one in the bottom, these are called bedding planes. You can read up a little bit. These are planes along which there has been deposition. Bedding planes are planes of deposition. They are indicated by mineralogical variations, size variations. There is a lot of ways in which you can find out. This is the bedding plane along which the bedding plane sediments were deposited. But there and here, these layers are the bedding planes between A, B and C layers. You see, they have angular unconformity is this plane that separates inclined sedimentary beds below beds which are horizontally deposited. Now you remember one thing. This is the erosion plane. So sediments normally deposit parallel to above the unconformity. They deposit parallel to the erosion plane. I mean, if I reverse this, it's not an angular unconformity. Because why? Sedimentary layers are deposited in horizontal layers. So say for example, if I draw a situation like this, Say. And this is top. It is impossible to do it. Why? Because these are the older sediments. The older sediments are horizontal, but younger sediments are inclined. It cannot be. It will, if this is such a process, this cannot remain horizontal, because initially it was horizontal. So if you have to have an inclined plane, because this plane also deposited on a horizontal plane, that means the horizontal plane of bedding has been rotated. You cannot rotate the above one without rotating the ones below. You can't do it. So this is wrong. In an angular unconformity, the lower layers are inclined or oblique to the layers above the angular unconformity. This happens because these layers here, as I have shown you, they were initially horizontal. They were initially horizontal. Then because of some tectonic forces, they were made inclined. And then there is an erosion surface. That means it came above water level. So there was erosion. And then the whole section went down and you have redeposition along horizontal layers. I will repeat again. The layers MNOPQ are sedimentary rocks. So they are bedding planes. So they must have been horizontal. After being deposited, they have been tilted. Can you see that? They have been tilted because of some force. And then you have the erosion plane. So the erosion plane means the rock strata was raised above the water level so that erosion takes place and no deposition. And again these have horizontal layering. That means again the section went down below the water and there was again deposition. So this plane remained as the angular unconformity. That means this was the zone of erosion. There are, in the internet, there are many sites which show this and describe this in great detail. So you can look it up. There are many books which will help you to look it up. But internet sites, if you type types of angular unconformity, will have wonderful photographs done by much better people who can draw much better than me. And they will also explain to you. Another type of unconformity is called disconformity. Disconformity. What is this? Here, this is a geologic section. Here is the unconformed. There are beds here, sedimentary beds above and below. A, B, C, M, N, P, Q. The difference from angular unconformity is that above and below the unconformity you have sedimentary layers, but both are horizontal. They are not angular. So between this and this, there is no tilting as you saw in the angular unconformity. No tilting of the lower layer. So this is what is called a disconformity. But what happened? A, B, C deposited in sequence, A being old, C being young. They were below the water level. And then it was raised up. There were some sections, I don't know what, because the record is lost. I can't tell you. But it was raised above the water. Why? Because I see the erosion surface. I see the erosion surface. That is why I'm saying that it was above the water level. And then again I see new sediments being deposited. So again it was brought down the section below the water level to have a particular set of new sediments. But what happened between C and M is not known. That record is lost. Whether it was lost because of discomfort or because of erosion, or whether it was lost because of non-deposition, can't tell you. Only difference with angular unconformity and disconformity is in angular unconformity, the lower strata gets tilted and then uplifted and then redeposited by newer sediments. Here, the tilting is lacking. Right? So, where did I leave my dust? Yeah. Now, I will leave one type of unconformity for you to read. I will not tell you that. It is a little tricky, and that is why I am leaving it to you. Paraconformity. Paraconformity. Have you understood? This I leave it to you with the only hint that it is similar in many respects to disconformity. It is difficult to separate paraconformity from disconformity, but I leave it to you to read what is the difference. Yeah? Right. Now, remember where we started from now. We wanted to study chronology of events, and we were talking of relative events, one relative to the other can be decoded. So, let me draw a section, a simple one, a very simple one to start with, so that we can see how things work. And we will try to identify the features. All our geologic sections, let's say we have such a geologic section. Right. What are the things there here in the geologic section? If you look, remember this is the top. Remember this is the top. That means this is the direction of younging of the rocks. This one here, the lowermost layer, you can see there are folds. Have you understood? I told you this could be because of metamorphic rocks, where a particular metamorphic layer is folded. So this is a metamorphic rock. It's a metamorphic rock. And this set is a set of sedimentary rock. Right? What is this? It is a fault, because it just faults the rock. What is this? This is an unconformity.
So it's below A and B. You've drawn it below A, between A and B.
Oh. Sorry, I am sorry.
No.
Oh. It was right.
Yeah.
It was right. Yeah. Thank you. Yeah.
Unconformity is below. That's it.
This is the unconformity. This is the unconformity. What is the type of unconformity here, if somebody asks you? This would be, there are three I told you. Let us keep it at three and not paraconformity. Non-conformity, angular unconformity, and disconformity. This contact is between metamorphic rock. This contact is of a metamorphic rock underlying an unconformity and a set of sedimentary rocks lying above the unconformity. According to the definition that I told you, this should be a non-conformity. It is a non-conformity. It is not an angular unconformity. Why? Because this is not a sedimentary rock. It's a metamorphic rock. Okay? Now, if this is so, then you have A, B, C and D. A is the oldest, D is the youngest. Now, I will tell you to be just careful. There are many ways to identify sedimentary rocks which are old and which are young. I will come to that later. At the moment, it looks like that whatever is below is A. A is oldest. Most of the time it is. But always it is not. Always it is not. I will give you an example. Say for example, there is a layer A and B. Somehow I know that A is older than B. Somehow I know. But let me do one thing. This is A and this is B. This is a section, yes? This is a section. Now, I fold it. That means, remember, folding, bending of rocks. I bend it. You see, in this part, this was original. In this part, the original chronology is correct. A is older and at lower height than B. Correct? No problem. But you look here. B is lower and the older A is above it. Can you see that? In this limb of this fold, A is older, B is younger, so above. Correct? But look at this limb. The older A is now above B, which is younger. Sedimentation wise, you cannot do it. Sedimentation wise, you can't do it. You can't deposit a younger layer below an older layer. You can't do it. Here, what has happened, the original sequence is inverted because of the geological process. So, you can have normal sequences and you can have inverted sequences. That is why, when I write here A is older, it does not mean that always what is lower is older is not correct. There are certain criteria which I will tell you later on. To unambiguously say which is older and which is younger. I am just telling you to be cautious. That's all. Because you are so young minds that you can have inversion of time also. But we will do that when you are a little more mature than right now. Yeah? So, this happens very commonly. Unless you are careful, you will make huge mistakes. But let us come to simple things first, without clouding your mind. Let me check the time here. So, this is an unconformity, which is a non-conformity, we agree. There are metamorphic rocks here, and there is a fault plane here. So, what was the sequence of events? What was the sequence? Which was the oldest sequence? The oldest rock were the metamorphic rocks. Oldest rock were the metamorphic rocks. Then what happened? There was an unconformity. There was erosion. Right? Erosion, unconformity. Then there was deposition of A to D. And then there was a faulting. Brittle deformation, remember? Brittle deformation. Faulting. What was the type of faulting? You can see, remember, there's an inclined fault. So this part should be the hanging wall that hangs on it. And this is the footwall. So the hanging wall has moved down related to the footwall. So it is a normal fault. And did you notice that looking at this, we have now placed the events in time. We have placed the events in time. First, there was production of metamorphic rocks that formed the non-crystalline crust. Then there was erosion of the metamorphic rock. That means the section went above the mean sea level. And then you had erosion and conformity. Then the sequence went down. There is a vertical movement of the crustal section. And you deposited sediments A to D. And then you had the whole thing was faulted. So this is the relative scheme of things that gave you this set of rocks. Okay. Different set of rocks. To add, okay, we will do it in the next diagram. But have you tried to understand this? Now let me take up another geologic section and try to show you how it works. We do it the reverse way. We do it the reverse way. In a geologic section, there is a non-conformity. There is a disconformity. And there is a normal fault. No, let me make it simpler. I think this is too much for you. Let me make it simpler. Let's say we have a disconformity. We have a normal fault. And we have a reverse fault. Have you understood? Reverse fault. Let's say the normal fault is younger than the reverse fault. Mark my words. I have told you, I see a disconformity. I see a normal fault which is younger than the reverse fault which is older. Do you get my point? I have to show this. Now let's say the normal fault is younger, the reverse fault is older. I take a section and I draw a disconformity. Do you understand? I draw a disconformity. See, you follow what I am doing. This is a reverse fault. Have you understood? It's a reverse fault. How will I draw the normal fault, which is younger? See, the fault, the reverse fault here is terminated by the disconformity. Terminated by the disconformity. That means to say, there were sedimentary rocks here, which I have not drawn, purposefully I have not drawn, and there is a reverse fault. That means, say for example, this was a sedimentary layer, and this sedimentary layer should be here now. Let me name this A, and let me name this B. There are other sedimentary layers. Without making it very complicated, I'm just putting one sedimentary layer, A. The movement is reverse fault. But it says reverse fault should be older. Fine. Relative to normal fault. What will I do now? How will I draw a younger normal fault? This question that you should ask me, younger to what? It is not defined. Younger to what? If, say for example, the normal fault is younger to the disconformity. Have you understood? Younger to the disconformity. What would I do? Younger means that fault should fault the disconformity. So, I take it here. Do you see that? Do you see that, students? A reverse fault is older. Why older? Because the fault is truncated by the disconformity. Truncated by the disconformity. That means the reverse fault is older than the disconformity. And then you have a fault which faults the disconformity. That means it's younger. That means it's younger. That fault is younger. So now I have this situation. What is the time scale now? So let us now put another sedimentary layer here. Say, okay, I write this as B, write this as B, write this as A, write this as A, write this as C, and then M, N, and P. And I write this as N, M, P. Have you understood this? So, what is the sequence of things that happened? First, there was the deposition of A, B, C. Deposition. Of ABC. Then, fault reverse. That faulted A, B, and C. Is that right? Then, you have an unconformity. A disconformity. And then deposition of MNP deposition. Then fault. No. Again you see, I have timed the events. I have timed the events. I can't tell you when it happened. When it happened in the Earth's record. But it happened sometime. It happened sometime. Now I think I will be running out of time. So I will give you a problem which you try to solve and send it to me by Classroom, Google Classroom. You send it to me. Here's the problem. Draw an angular unconformity. Draw a section showing an angular unconformity, a disconformity, and a nonconformity. You draw it yourself. Draw a section showing an angular unconformity, a nonconformity. And you tell me what problems you faced, because you will face a problem. I will answer your questions later on, but first you should draw a section of one section where there is one angular unconformity, one disconformity, and one nonconformity. That's it, no faulting, nothing. But you will encounter a problem. If you are a good student and working hard, you will encounter a problem. I want you to tell me, what problem did you encounter? Right? So, I stop here for this slide.